All right, cool. You're good to go. So group 4, the floor is yours.
Hello, everyone. Welcome to Group 4's presentation on our heliostat, the Accustat. Our team members include James Beard, Moises Castro, Jerome David, Hunter Enos, Natalie Lopez, Marvin Portillo, and Brianna Renda. Next slide. So for a general outline, first we'll start off with our introduction, go into product overview and functionality, go into some subsystem breakdown, and wrap it all up with a summary. Please note that there are page numbers on the bottom right. So if you have any questions, please make sure to keep that page number in mind.
As the name implies, the Accustat is intended to accurately track the sun's movement across both azimuthal and altitudinal angles in order to reflect the sunlight towards a central tower in a concentrated solar power plant. Key to our design are two elements, our actuation and tracking systems. Our actuation system aims to minimize the smallest possible angle that our heliostat can move in order to accurately reflect the light. And the tracking system works in conjunction with this in order to make sure that the heliostat is properly oriented towards the sun. It does this through closed-loop feedback tracking control. Compared to open-loop tracking control using solar positioning data, this makes the alignment significantly more accurate. How have we done that? Let us proceed to examine our system as a whole on the next slide.
So for a product overview, our design is broken down into four main subsystems: base, actuator, reflector, and tracking. For a max overall configuration size, our design is 2.1 by 2.1 by 0.78 meters. We have one main computer per module. We have a 2-motor system per heliostat, as well as gears, and we have an attachable camera mount to the central tower. We chose to go with 4 heliostats over a greater number due to the driving cost of the motors. Next slide. So for basic functionality of our tracking system, it is actuated by our 2 motors with the gears, and the tracking is done through our camera and edge detection software, which is then sent to our control board, which directs the heliostats, and that is connected to a central computer over Wi-Fi. Next slide. So our 4 main subsystems: base, actuator, reflector, and tracking, and we'll go into the breakdown in the next slides.
We begin with our base subsystem. It's designed with several customer needs in mind, ensuring that there's no shading between heliostats, system stability in high winds, and low cost through easy assembly and low amounts of material. Our base is designed low to the ground, yet wide enough to stop shading, yet small enough to maintain a small reflective to ground area ratio. It's made of a readily available steel tube, simply welded together and inserted into the ground. Next slide. Our design began life as a very simple table-like structure. We had designed 4 vertical posts. It's industry standard to use concrete in order to secure these into the ground. However, concrete's rather expensive, so we determined that we could provide extra support with cross beams. However, there are some issues with this design, notably that the heliostats don't have full orientation, and it's not very easy to mount the heliostats into here. So we revised this design. Next slide. By moving the crossbeams down to the ground and burying part of it in the soil where the crossbeam sits at the bottom, we are able to provide shafts to mount the heliostats on and provide full movement. And by changing it from solid tubes into hollow tubes, we are able to lower material costs even further. Continue to the next slide.
To pick up now where Jerome had left off, I'm going to kind of walk through how we came up with this exact design, our parameters, dimensions. The entire design is primarily driven by these 5 variables you see here. The easiest one, the first thing we tackled, was the height of the pole above the ground, which we found only needs to be about 1/4 of a meter, which is half of our reflector length. And that is because at that height, since we're mounting at the center of our reflector, the reflector clears the ground, and it'd be unnecessary and costly to have it higher than necessary. But our biggest things that we had to determine was the spacing of the heliostat and the width and tube thickness of the poles. So starting with the spacing, this was entirely dependent on the shading customer need. They specified no shading. However, with all of our heliostats mounted at the same height, ideally, at 0 degrees when the sun first comes up, there's going to be shading. You can't avoid that. So we had to set what time of the day we wanted to start our collection, time. And so the plot on the top right of the screen shows you sun plot for Las Vegas, Nevada, green being the longest day of the year and the blue line being the shortest day of the year. And using this, we set a target of 20 degrees to 20 degrees, which would give us about 5.5 hours of daylight, or not daylight, 5.5 hours of no shading on the shortest day of the year. Using the equations here and the steepest target angle, which would be a 45-degree angle, being your farthest heliostat from the tower on the side opposite the sun, we're able to use these equations to get the minimum spacing necessary to have no shading at all. Now, going in on this picture at the bottom, these are different configurations that we were looking at. If you have a 20-degree sun angle and you have on the left side is a 45-degree target angle, which, like I said, is going to be your steepest on the side opposite the sun. And on the right side, you have your closest heliostat on the side of the tower, same side as the sun. You would need almost a 1.5 meter spacing to achieve no spacing at 20 degrees, which frankly was just a little much for us. It really increases the cost to space them out that much. And we didn't really want to go about that, go that way. But at 30 degrees, you can achieve no shading at under a meter. So essentially we went with the 1 meter compromise, which you may be thinking, well, look at the plot. That's not, that reduces our hours. However, one thing to keep in mind is that that does not necessarily mean that just because there's some shading doesn't mean that the entire heliostat becomes useless. As you can see in these graphs, at 20 degrees, over 30% of the field experiences no shading at all. And the other 70% of the field that experiences some shading, you can see that the maximum shading occurs is only between 30 to 35%. That's what this picture on the bottom is. It's your furthest, most shaded heliostat. So in another way you could look at it is by 25 degrees, half the field experiences no shading at all, and the other half experiences a maximum of 15 to 20% shading. And you have an overall efficiency of, still 80 to 90% by 25 degrees in the sky. And so we kind of had to come to that compromise with the spacing. Now the other parameters, the width and the tube thickness all came down to our wind force analysis. You can model it as a cantilever beam with the point load at the top of the beam being where our reflector is mounted, and the force being the wind force on the reflector, and the force on the pole at approximately half the height of the pole. And so using the equations on the left, you have bending moment and your bending stress. You can get factor of safety as a function of that width, thickness, and material property. And so using the customer need statement that everything needs to have a factor of safety of 2, and using a maximum wind speed record of 90 miles per hour for the Las Vegas area, we were able to calculate the minimum width that our tubes would need to be with various materials, and then compare the costs of those. So for example, aluminum, since it's a little bit weaker, you would have to have a little bit larger of a pole. That would be a different cost, because aluminum costs different, and to have a bigger pole costs different. And at the end of the day, we found that a 3/4 by 3/4 18-gauge steel square tube would be the most cost efficient while providing the necessary factor of safety. Now, our design in our diagrams at the beginning, that showed a square, looked different than the picture at the opening slide. And that is a slight design change that we made, was while keeping all the parameters the same, the tube thickness, the wall, the height, the spacing, we were actually able to reduce material by using the diagonals rather than perimeters. Other changes we made were we shortened the height of the pole above the cross beams, because we realized that the actuation system actually adds about 3 to 4 inches of lift to lift the reflector up. So we were able to remove that material and lower the cost. And we were able to remove the gussets based on some calculations here. Originally, we were using welded on gussets because we thought it would, need more support. It added a lot of cost, and so using moment equations, you can find the reaction force at the top of the cross beam, which would be higher than your reaction force at the bottom of the cross beam. And then using the width and thickness of that we already determined, you can find the tensile stress in that weld joint. And after doing some research, we found that welds are actually as strong, if not stronger, than the parent material itself. So you can use that same yield stress to compare, and the stress that it would go under would be, low enough that it's not going to fail. So we were able to eliminate those gussets for actually reduce about $8 in cost. And so our final specs, after determining everything, is we have a bending stress factor safety of 2.8, the weld factor safety of 2.4, and our beam deflection, the top of our pole in the highest winds, 90 miles per hour, deflects only 1.36 millimeters. And the cost is $18.17 for the stock material.
Hello, this is our Actuator subsystem. It is arguably the most complex and equally important part of our entire design. This is because it does the job of actually retaining the motion, allowing the heliostat to perform its job to track the sun and point the light at the central tower in order to generate its purpose of creating energy. So it has to satisfy several key concepts. It has to be able to rotate about the azimuth and elevation angles, which we actually have a full azimuth rotation of 360 degrees capability and a 180 degree elevation capability rotation, which exceeds the customer needs of having at least 90. We need to have our gears be able to hold the reflector stable in the winds of Las Vegas, because ultimately what's going to fail first is what's going to affect the design's ability to perform is going to be it being full of errors, it moving, it basically deviating from what it's supposed to be able to do. So we have gears that increase the basic holding torque of the motors to a capability that is respectable enough to handle the wind forces in the environment. We made sure it's small and compact because otherwise it would interfere with the rotation of the reflector around it or require a much bigger design and introduce more stresses. We made sure it had to be low cost because, as it's the only part that needs motors, it's going to be the most expensive as well. And we had to make sure that it was going to be structurally stable, able to perform and stay intact, which we actually determined to have a factor of safety of above 2 actually, in order to make sure that the design performs the standard. We can move on to the next slide. We had an original concept where it was a sort of modified gimbal. You can see here that we have the issue of it being much too large and having to require an extra extended part off that horizontal shaft to not interfere with the edges of the brackets, on either side. It also solely depended on the strength of the motor rather than using any sort of gear reduction to increase the torque, meaning that the 0.4 Newton meter output that we had with the ordered off-the-shelf motors was not going to be enough to perform the standards and satisfy our customer needs. So we had to change that to a gear reduction system, as you can see on the right. It also, if you look at the red encased motor acting vertically, that goes directly into the base of the design. And that means any forces that act on it that would normally translate to base must go through that motor shaft, implying that there would be a bending moment at some point on the motor shaft, which is of course taboo. And finally, based on how much of the ASTM A500 grade B steel we used, we would need a total of $55, not just the motors, but for the bearings and the entirety of the raw steel it would take to manufacture this part for all four of the reflectors. On the right, we managed to actually decrease that by $10, despite having more screws, more gears, and a more solid bracket. We can move on to the next slide. So this is basically the assembly of it. So you can see we have the 2 standard NEMA 17 stepper motors that actuate both the elevation and azimuth changes, and they are enclosed by the motor enclosure in order to make sure that we do not expose it to the outside environment, and we can actually wash it without damaging the electronics. we have the bearing that fits into that large hole you can see in the upper portion of the mounting bracket that allows any forces acting on the reflector to translate directly into the mounting bracket instead of down onto the gear you can see and act on the motor. This is similar to the rod we have at the base there, which actually prevents the bending stress from acting on the vertical NEMA motor. So they all fit into the slots, as you can see there. We had exploded lines that probably be even more visually appealing, but that's how it all comes together. We can move on. So to talk more about that rod that allows us to avoid a bending stress that the original design had, we created a large gear that is lets the actuator actually sit and attach to the base, the square tubing of the base frame through a press fit. And within that, and it houses a bearing that fills that small gap you can see on the right between the mounting bracket and the transparent portion of the frame, which allows the housed metal rod you can see to translate all the forces directly from the bracket down to the frame without interfering with the gears, without interfering with the motor shafts. And it also makes sure it's a rigid object, therefore everything acts smoothly and rotates stably. We can move on to the next slide. So you can see further, this is an actual animation of how our actuation system works. It can rotate 180 degrees about that the large gear you can see there. And the smaller motor actually crawls around the larger motor. The larger motor is stationary in order to make sure it's stable. And the smaller motor being placed away is what allows us to avoid the whole bending stress issue I mentioned earlier. We can further move on. So one of the biggest things that comes into this design, the largest portion of any kind of stress analysis, is what the wind does to our design, because we essentially have a large object catching a ton of wind and acting on our small components. You can see that at the moment we actually have the reflector acting as similar to an airfoil. We found that the maximum amount, the point at which maximum force acts on the airfoil that is a reflector is about a 10-degree incline. And it acts at about one quarter of the chord length, or about one eighth of a meter away. And so from these calculations, we actually find that through the increased torque, holding torque that we get from the gear subsystem, we actually can sustain wind velocities of up to 19 miles per hour, where the average wind velocity is about a bit less than 10 miles per hour. Meaning that we can operate in most conditions except emergency conditions. So we can move on to the next slide. These are the figures that the next calculations will be referencing. You can see the bracket on the right. The second from the right is the reflector in its most extreme wind catching position, and then two more views of the bracket on the furthest right. Move on. The systems we have two sorts of stress acting on it. We have the force from the reflector acting onto the bearing, where the shaft intersects with a bearing that puts it into the motor bracket, and that's what the biggest stress acting on that's probably the largest stress acting on the entire actuator subsystem. The only other one is if wind comes from a perpendicular direction to the reflector, it would act on the small vertical face you saw the mounting bracket, inducing the other force. Or respectively, force of the wind on the reflector and force of the wind on the motor mount, or the force of the wind on the motor mount. Yeah. And we find out it survives plenty. We made this out of steel, so it actually has plenty high yield stress to withstand this for the full operating lifetime. We can move on further.
So one of the concerns we had is one of the problems we ran into, gears are rather expensive to try to purchase. And so we are considering custom making gears. And the best way to custom make them would be if they were out of plastic. You can 3D print or injection mold them. And so the only thing we were concerned about was if the teeth on the gear would actually be able to withstand the torques and the high winds. And so this is a brief analysis of the bending stress and the pitting / contact stress. One of the things that actually decreases is since they aren't, typically gears are moving very fast, go through several cycles at a time. Essentially, since this would be rotating, over the entire day, a portion of a rotation over the day, and then reset at night, you can assume it to be, 2 cycles a day. And so there's going to be the wear on it, which is what the pitting and contact stress relates to, would be very low. And both of these numbers are extremely low compared to their respective material properties. And a small little detail that we want to highlight was how we were actually going to secure the pinion gear to the motor shaft, because again, with plastic, we are concerned about it, wearing down and breaking and holding. And so you could design the gear to have a D-shaped hole that would fit around the shaft of the motor, but we are concerned that in the torques and the high stresses it would be under, that the motor shaft would actually wear out the center over time. And so the second option would be putting in a set screw. But again, we were into a threaded hole in the gear. But again, we were concerned about the thread stress, maybe stripping the threads in the gear as you were either clamping it down or again, just over time. So a solution that we came up with was to house a shaft collar inside the gear that would place all the thread stress responsible for clamping onto the motor shaft on the metal threads. And this essentially is 2 pins acting at perpendicular axes, which creates a locked structure that the gear cannot rotate about. It'll also be, like a press fit. So that eliminates all, worries about the motor shaft wearing out the gear.
Now on to the reflector subsystem. So we chose a 0.5 meter by 0.5 meter, 2 millimeter thick acrylic mirror for each heliostat. And we are using 4 heliostats per module, which gives a total collection area of 1 meter squared. There are a couple of reasons why we chose acrylic over their regular glass counterparts. First of all, acrylic is very lightweight. An acrylic mirror has a density of 1.19 grams per centimeter cubed, compared to glass, which has a density of 2.45 grams per centimeter cubed. This weight reduction places less strain on the actuators, which will allow them to have a longer lifetime. Additionally, acrylic is also very cheap. A 1 meter squared sheet of 2 millimeter thick acrylic mirror can be purchased for $1.44, whereas a 2 millimeter thick glass mirror can be purchased for $3.10, which is twice the amount of the acrylic. Acrylic is also resistant to breaking. In terms of impact resistance, acrylic mirrors are 17 times stronger than glass, so it can survive greater impacts such as collisions and crashes without the concern that it will shatter. Acrylic mirrors are also washable. They do not react to water, cleaning soaps, or environmental elements in a negative way, so they can easily be wiped down with soap and water. They are also highly reflective, which we have calculations on in a few slides. And although acrylic mirrors are strong in terms of their resistance to breaking, they are also very flexible, which is why we included an aluminum cross support to avoid bending. And the acrylic mirror is also screwed directly into the support and the rest of the assembly, whereas glass is harder to drill holes into without the risk of splintering or shattering. And then if we go to the next slide, we can see our design progression. So originally we had the acrylic mirror mounted on a 0.5 meter by 0.5 meter, 25 millimeter thick base made of 6061 aluminum, which we decided to change to the cross support subassembly, which is 3 millimeters thick and consists of 2 bars that are 255 millimeters long and 25 millimeters wide. The first design is much more expensive, with the cost of just the mirror and the support coming to $6.03, whereas the updated design has a cost of $3.84 for the mirror and the backing. The first design has excessive support material, whereas the updated design has a more minimalistic design. We concluded that we could still achieve our desired level of stability by reducing material and saving money. And the first design is much heavier than the updated design as well, which would put more stress on the actuation system, which is another advantage to the updated lightweight design. And then if we move on to the next slide, we can see an exploded view of our reflector subassembly. It consists of the 0.5 meter by 0.5 meter, 2 millimeter thick acrylic mirror, the reflector support subassembly consisting of the 6061 aluminum rectangular bars. And then to connect to the actuation, we have the reflector gear subassembly consisting of a reflector attachment made from aluminum and a 48 tooth reflector gear made from ABS plastic held together with 2 gear screws. And then we have an aluminum rod, which connects to another aluminum attachment, and then stainless steel reflector screws to hold everything together. On to the next slide, we have reflectivity. In terms of reflectivity, acrylic mirrors have an optical efficiency of 90%, which is very optimal. The thermal input constant can be calculated by multiplying the solar constant by the total collection area by the optical efficiency, which yields a value of 900 watts for one module. On to the next slide, we have bending stress. So for bending stress, we assume that the worst case scenario for the mirrors would be when the mirror is in its most vertical position. We calculated the wind force and bending moment that half of the mirror would experience and then doubled it to account for the other half when calculating the bending stress. So for the maximum wind speed that Las Vegas experiences, which is 90 miles per hour or 40 meters per second, the bending stress was calculated to be 233.9 megapascals. This is much larger than the 76 megapascals that an acrylic mirror can withstand. However, since the heliostats will enter a safe mode in which the mirror will become horizontal once the winds reach 90 miles per hour, this will not be an issue. Running through the same calculations for 90 miles per hour or 8.5 meters per second winds yields a bending stress of 10.4 megapascals. This is the top wind speed that the mirror will have to withstand while vertical, and this gives a factor of safety well over 2. The calculations for the average wind speed of 8.5 miles per hour or 3.8 meters per second yields a bending stress of 2.1 megapascals, which the mirror can easily withstand. And then on to deflection. The deflection due to the wind also needs to be considered as it can affect the amount of sunlight that the target receives. This deflection is also going to be observed by looking at the mirror when it is in its most vertical position, as that is when it will experience the most straight-on force. So then the deflection due to the 90 miles per hour wind comes out to be 106 millimeters, which again won't be an issue since the heliostats will enter a safe mode after 90 miles per hour. The deflection due to the 90 miles per hour wind is 1.5 millimeters, and the deflection due to the average wind speed of 8.5 miles per hour is 0.315 millimeters, both of which are relatively small. And these deflections occur when the wind is hitting straight on, so most of the time these deflections will be minimized and negligible. So next slide.
All right, finally, we have our tracking subsystem, and here are some key features. First off, we have the camera which is being used, which is the Nikon D2X camera. This is an older camera, but it still has all the capabilities necessary for capturing quality photos. And the camera will be used using a Lowell Venus Optics 25mm lens. The reason this lens was picked was for its focal length, which will allow it to view heliostats as close as 30 meters away from the central tower, and as far as the maximum 100-meter distance, and it will actually extend a little bit past that 100-meter distance. Next up, we have the sheet metal mounts. Oops, sorry, can you go back? We have the sheet metal mount, which is there for weather protection. We want to protect the assembly from rain and other weather effects. So it surrounds the camera on all 4 sides. These mounts will be mounted to all 4 sides of the central tower. So we'll have 4 of these total. Each one will cover a quadrant of the entire heliostat field. The accuracy due to the edge detection software is very high. It's about 3 milliradians on average, and it provides closed loop feedback control. All right, here we have a exploder view of our assembly. As I mentioned previously, it has the sheet metal mounts, the mounting screws, which will connect it to the central tower, the camera itself, and the camera screw, which is the portion which actually holds it onto the mount, similar to that of a tripod screw. Next slide. Here we have a description of our edge detection software. So in terms of how the edge detection feature works, it's essentially going to be a comparison between measured values by the camera, measuring the length of the heliostat in terms of pixels, and then calculated angles, which are determined by heliostat azimuth and elevation angles using the central projection. So the figure on the right displays the side lengths necessary for calculating the angles, as seen in the equations on the left. With those 3 heliostat edge lengths, in terms of pixels, we could determine the angles between the sides and the side ratios. So with those, once those have been determined, these values are subtracted from the values which are calculated from the azimuth and elevation angles. Then the azimuth and elevation angles can be changed until the difference between measured and calculated values are minimized, and thus the function below is maximized, giving you optimal accuracy. Next slide. Here we have an analysis of the wind acting on the camera mounts. So a bit more information on the sheet metal itself. It's 6061 aluminum, which is about 1 millimeter thick. And the stress was measured as if when we're acting perpendicular to the top face of the mount. So from that maximum wind force, which we've mentioned, multiplying that by the area gives us a wind force of 98 newtons. With that, we could find our bending moments. And then once we found the second moment of area of a square tube, which is the shape of the mounts, then the maximum bending stress was found to be fairly low, 0.652 megapascals. Next slide.
So now that my groupmates have introduced our various subsystem designs, let's consider their different costs. On the left side of your screen, you see the subsystem materials costs organized. And as you can tell, the actuator accounted for over half of the total subsystem material cost. And that total was $80.50. On the right side of your screen, you can see a pie chart that organized all the costs that contribute to the overall cost of our design. That accounts all the subsystem materials as well as any manufacturing, assembly, and energy consumption costs. And it's important to mention that shipping was not considered in any of these costs because we figured that they could be greatly bargained for, and it depends on the amount of items that were ordered or any connections that the customer might have.
As you have seen, we put a lot of careful consideration into the various aspects of our design. However, there are some elements that have received special consideration. The decision to switch from the industry standard glass mirrors to acrylic was done to have cheaper, lighter, and sturdier mirrors, which put less of a strain on our actuators, which use gear reduction and stepper motors to allow for minute angular movements that make the Accu-Stats accuracy possible. To top this all off, the tracking system implements closed loop feedback through image processing. That means that our design will reflect light more accurately than any other proposed design. But why do we have these special considerations? Next slide. In a word, efficiency. As many of you know, the viability of an energy source comes from how much it costs to produce a kilowatt hour of it. There's no real point in having a concentrated solar power plant if we cannot get this number below that of other renewable energy sources. Many of the other proposed designs for these heliostats have tried to do this by cutting costs, using materials like wood and PVC, lowering the number of actuators, anything to grow that bottom line. And we've certainly done our fair share of that with the reflection system and the base system. But at the same time, we determined that we can bring this number down also by bringing the amount of kilowatt hours that our design produces up. These minute losses in accuracy over a 20-year period do build up, and the Accu-Stat minimizes these losses by being more accurate. So we are asking for a little bit more money than some of these other designs, but for a whole lot more power generated. Other groups have also noticed this. There are some other groups that do include closed loop feedback. They basically do this through motor encoders, which in addition to being slightly less accurate than this image processing method, also costs a significant amount more. The Accu-Stat competes with cost cutters in terms of cost and beats out the other competitors in terms of accuracy. Next slide.
So overall, some key takeaways for the Accu-Stat design are that firstly, it's an extremely accurate design. We are guaranteeing a 3 milliradian uncertainty level. Additionally, we've optimized our frame designs to reduce material amount, which in turn reduced our overall cost. Lastly, we have lightweight, low-cost acrylic mirrors, which are changing from the industry standard, but are more effective in our design and help the motors last longer, as well as offer a lower price. And lastly, we'd like to say thank you to all of our corporate sponsors. Thank you, Cummins, Northrop Grumman, Carrier, and Argo for your support. Additionally, thank you, Professor Nimi and Trom, for guiding us throughout this process.
Excellent. Thank you guys very much. We will go ahead and open up the floor for any questions from our panel.
While your panel is warming up, can I ask a question or two?
Go for it. You're a part of the panel.
Okay, well, I confess I'm not filling out the grading rubric. But tell me about how you got your uncertainty calculation. What is that based on?
The uncertainty for the tracking.
Yes.
So the tracking method is based on some research that's been existing for a while, specifically a research paper. And in their work on this method, they found that in 50% of situations, the uncertainty was 3 milliradians or less. In 80%, it was 4 milliradians or less, but we decided to go with that 3 milliradian value since it is in 50% of the situations. And it does vary depending on where heliostats are in reference to the camera and different factors such as that.
Okay. And that might be based on something that isn't as as flexible as yours, compliant. So first of all, I have to say, what I like about it is I really like that you are closing the loop from the endpoint. It would still be good if we had limit switches, so we could at least start up okay. But there are many factors of error that are going to affect what you see at the tower. And so you're sort of closing that loop, but there's some that you might not be able to account for. Like I did love your wind equations, and it was great that you calculated the stresses and would you meet the stresses. But since you've done all that work, maybe you should just take a peek at what kind of reflections, deflections you are going to see at those wind speeds. If you were responding to a constant wind, then your closed loop system could account for that. But if you have, a gusty wind where it sets up a resonance, then you're probably going to get some kind of instability in your feedback. Have you ever driven on the Solstice on a east-west road, like morning commute?
I can't say I have personally. I don't think so.
Okay, so have you ever driven and been looking straight into the sun?
Yes.
Okay, so I have a feeling that your camera is going to have an issue with being able to detect, during the bright sunlight, even if it's not at the point you're aiming the mirror, it's still going to be bright and shiny and probably not able to do the edge detection if, at all, well, if at all. So I don't think you're going to get the same results that, tell me a little bit about that study. Was that based on a heliostat?
Yes, it was specifically
Wow.
for heliostats.
Well, I'm impressed. Did they use filters?
Filters for the camera?
Yeah, so, trying to filter out, such intense sunlight, so that, kind of essentially sunglasses.
Right. Yeah, they did. They changed
Okay.
the RGB values to certain RGB values, which kind of enhanced the edges, which made it easier to detect.
Okay, so and I assume that will be put into your camera system. Well, that
Yes.
is great.
Thank you.
Great. Anybody else? Apparently, Dr. Tong's going to be in Las Vegas on the winter solstice. That's exciting. Rick, did
So
you
this
have
is
a
Rick
question?
Miles with Northrop Grumman. I got a couple questions. So with the, it's interesting approach, definitely different than some of the other groups have taken with the camera tracking system. I kind of had the same concern with being able to actually pick up the edges and with how bright the reflection would be off of those. So with your 900 watts per module, so is that, when you say module, is that a group of 4 or is that each individual one?
It's a group of 4.
A group of 4. So your area that you're taking up is a 2.1 meter by 2.1 meter field, and you're going to need what, about 1,200 of these to get your 1 megawatt of energy that you've got to produce. It's going to be a pretty wide field that the spacing is going to be taking up, correct?
So it was assumed that from the customer needs that they could extend up to 100 meters from the tower. And so if you had a radial pattern, plenty will fit in that area.
Yeah, so it was the camera the constraint on why you kept all the heliostats at the same height? Because it seems like you could compact them together a little bit better if you had them at staggered heights instead of all at the same height.
So the reason that we had them all at the same height was for the shading reasons. Because if you have them at staggered heights, then there comes a point in the day after the sun crosses, straight up, that you essentially would be increasing, like you would have better, you would have less shading as the sun, say, rises for certain heliostats, but then when the sun sets, because of that staggered height, you would have a greater shading effects. And so we decided to do even level heliostat mounting in order to, because we figured it would probably be better to get as much sunlight as we can hitting them, rather than design it to block out the sun by the end of the day. We wanted to avoid, that guarantee of, okay, well, if we stagger them, make them higher, that's going to block the sun once it gets to the other side of the sky.
Okay, yeah, I did appreciate the walkthrough of the shading for the different angles. I thought that was very informative, very nicely done there. And then I had the concern with the plastic ABS gears wear, and you did address that for attaching to the collar, but I would be concerned with the teeth wearing over time and how that's going to hold up through the life of the mirror, and how much maintenance that's going to require as that wear happens. I don't know if you have any data on that.
So this is what we have in the slides right now. I think we do a little bit more in our report, but essentially, as far as the bending stresses, that is extremely low. As far as wear over time, one of our this here, the sigma C is the contact stress, which if you have metal, you can compare it to the hardness, the surface hardness of the material. So for example, cast iron is about 32% of the brittle hardness. For plastic, that is the flexural rigidity of it, which I believe is around 80 to 85 for plastic. So this gives us about a 2.5 factor safety for, when it's in contact. Now, over time, those effects are going to, build up. You're going to have, it's going to slowly wear. But one of the things to keep in mind is that these are moving, in contrast to normal application of gears, these are moving extremely slow and only come to contact twice. Every one of the teeth come to contact only twice a day. So, because it would move throughout the day and then have to reset at night. And so that's one of the things, this KV velocity factor, velocity being 0, that cancels. You're going to have probably a similar effect with the wear, is it's going through such a minimal amount of cycles, you can say, that we can expect a long lifetime. And if there is a chance that, or not if there's a chance, if there's a need for it to be replaced, the one thing about it being ABS and either 3D printed or injection molded is that they could be, mass produced for a very cheap cost. And, the cost for plastic is extremely low. If one of them gets weared out, it'd be a easily replaced item.
Okay, and then the last question, I'll let somebody else ask some questions. The feet, the 4 feet that are holding the mirrors, how are they constrained within the soil?
They are basically hammered down. We decided, since it's a hollow tube, the amount of sand and other ground materials, just dirt, small rocks, would be enough to compact around the base, around the lower segments of each foot of the base subsystem, and additionally it would fill the tubing since it is hollow, and that would basically create a almost weighted unified design, so it would become almost one solid piece with the ground. In addition, that cross section is going to be partially sunk into the ground, so it gets even more of a spread out frictional surface to reduce motion and shaking or changing. The only thing that could possibly do it is if you had the maximum wind situation and all the heliostats were pointing it in that direction to try and shift it in the slightest. But we obviously have the emergency formulation where the heliostats go flat in order to prevent strong enough winds that would dislodge it.
Quick
real
note
quick,
on that too is we wanted to, normally ways that you can do this is you put them into like a concrete cement pad, or you could just, if you didn't want to do the concrete, you could plunge the poles like really deep. And so we wanted to eliminate as much material as possible, which is why we came up with this cross beam structure. The depth that it goes into the ground is primarily there to keep it from shifting like laterally. And you have an entire rigid structure that keeps it from shifting or leaning because that, not to say lack of depth, but lack of depth as far as, how far normally a pole like this would have to be cemented if it was standalone. And so if it was a big concern, you could put like a little, like a pot-sized amount of concrete at the bottom if it became a big concern, or in testing it came out to be but it would be a dramatic decrease in having an entire concrete pad. But we don't assume that to be an issue.
Okay, and then sorry, I need to can you go up one slide?
One slide, this?
Yeah. Okay, and then back to the slide you were on. So this bending factor of safety of 2.8, how are you assuming that it's being loaded up to get that factor of safety? Like what's your critical load case?
This one here, we modeled it as a simple like cantilever. And so if you have a 90-mile-per-hour wind on the reflector at its vertical, which would be the most force acting at the top of the pole, because that's how we have it mounted, and then the force acting on the pole itself, we did a bending moment and bending stress equations for this bottom part, because that's where the maximum stress is going to be. Okay,
so you have no safe position for the max winds. You're assuming that it can take the winds directly on 90 miles an hour.
Our safe position would be flat to minimize the effects. We use this as a worst case scenario if something hit it and rotated it, if there was a certain like an up gust of wind or something that would rotate it. We wanted to design it to essentially take no damage. It was similar with our actuation system, like using the plastic gears. That's why we wanted to have metal connection points like between the reflector and the actuation system to take on that wind stress. So we use this to calculate what our sizes would be, but our safety configuration would be flat.
Okay.
Brad LaCroix here at Northrop Grumman. What was the total cost again? I saw the summation on the slide, but it seemed like with 8 motors, you would have more than a cost of $45 for just the motors.
That was sorry.
Is that per one of the 4?
No, that is per all 4.
Okay.
You can see the actuator is $45, which trounces even the other 3 combined. That is because of the motors. We ordered them from, I believe, either Alibaba or AliExpress. So you're able to actually get a discount on shipments in bulk. So we assumed you're getting 1,000 modules of 4 reflectors, and so that brought down the total cost. And in addition, we have pretty low strength and low torque motors, and that helped us keep the cost down too, because if you went even a fraction higher of the 0.4 Newton meter torque it had, it would become much more expensive. So based on the fact that we get it from a third party, we're buying it in bulk, and that we're using we're using the plastic, much cheaper gears to artificially increase that ability to perform, it keeps us under cost. It keeps our costs so low because of that. It's a combination of several, discounting methods almost.
Okay, and then you have two costs shown here for the total cost is,
Yes, so the cost on the left is for the material and the parts itself. So it doesn't, the one thing it doesn't include is like shipping, which we do have a cost breakdown of it if you had questions. Like the base comes out to be about like $3 for shipping. But the cost on the left includes then the manufacturing cost, our assembly cost, and our energy consumption. And the reason we kind of
Okay.
split those up is because the cost for the materials is kind of, it's set. It's like, you know, the price for the aluminum or the steel bars aren't going to change, but there can be ways to source out manufacturing, lower them. You can, on some of the websites, the shipping said negotiable. So we didn't want to put hard values on those because those can change, but we do give an estimate. So.
okay.
Yeah. We're going to have to wrap up here. We've gone a little bit over, and we are now digging into the lunch break, which I'm sure everybody is greatly anticipating. So thank you guys again very much for the presentation. Thank you for the sponsors for coming and for asking the questions. And we will go ahead and wrap up there.